Good morning, everyone. It's a great pleasure to be here. It's first my task to thank Barbara and Patrick. It takes great care to put together a workshop like that. I want to give a few thanks comments. I will review a lot of material basically assembled over the last almost 10 years, and there are many people involved in that. And many of them are working in terms of computational infrastructure. Many of them have been working on very technical mathematical aspects. Many of them really have been working on observations. And I've been very, very careful and grateful to work with outstanding colleagues. So I really want to give my thanks to many of them, but in particular, today I want to give thanks to Lorenzo Colli and Zia Gelichkan, because I really show most of their work today. And so both of them are in the back. Zia and Lorenzo, many thanks. Lastly, I should give a few credits. I'm showing expensive computations today. So the Leibniz Rechenzentrum in München funds us very generously. I have been involved in two large collaborative programs. One is the DFG program on the opening history of the South Atlantic. The other one is our sister program called Topo Africa, and it was run here out of France. Both really concerned with understanding the evolution of topography on continental scales over the last 100 million years. This has provided a lot of opportunity for me to talk to geologists, and that will inform much of what I say later. So, brief outline of my talk. I'll give a quick introduction that can be very quick. I will review a little bit of theory that we're developing for geodynamic models. I will apply that theory largely in terms of simple twin experiments, but also in terms of more complex, more realistic Earth models. And if I have in my 24 minutes time, I get to the very last part of showing retrodictions for fairly high and recent resolution models. And I will conclude with a few thoughts. This is a quick slide. Computational geodynamicists have made, I think, a great progress over the last 20 or so years, right? We have by now a large number of convection models. They have very high resolution. They have great computational efficiency. They allow us to do all kinds of scenario simulations. Where do the frontiers lie? The frontiers really lie in bringing these models much closer to the geological record. And in particular, these models involve, often whether we know this or not, long-range extrapolations, and they involve ad hoc parameterizations. And I'm very grateful to Patrick, because Patrick really brought this to my mind in a way that I had not really appreciated. And so it becomes really important for us to think carefully of how technically we would want to test our computational models in the future. And of course, the obvious way to link them is to link them to observations of the past. And in the past, classical forms of observations are the evolutions of sea level and past shorelines. This was brought to geodynamics essentially early on by colleagues like Jeremy Trevico or Mike Gurnes. And all I want for you to see through is when we flip through this, basically we realize that there's a lot of vertical motion presumably going on the continent that allows the development of inland seas. And of course, when there is so-called negative dynamic topography, there should also be positive dynamic topography. And Africa is an outstanding example for that. So many of you are aware that there is a controversy to the age of the high stand of Africa. Some people believe that much of this high stand is Mesozoic, essentially meaning 100 million years. Other people believe that this is Cenozoic, essentially meaning less than 30 million years. So there's a significant difference, and theorists should be able to contribute to that discussion. Of course, some of you are aware that some people believe there's no dynamic topography at all, and there's a recent paper in Tectonics in which basically the absence of any free air gravity anomalies over Africa is used as an indication that there is no free dynamic topography over this. But of course, this involves the assumption of a simple rule of thumb, which is common in tectonics. There's nothing wrong with that. It's just a common rule of thumb, 50 milligauss per kilometer. But of course, that means effectively it doesn't matter where density anomalies are located and what scale they are, they would always produce the same amount of gravity anomaly. At the same time, geodynamicists use the very same form, because these two are just two different representations of the same data, and represent this as a geoid anomaly. And we are aware that there is a major geoid anomaly over Africa, and so that would traditionally lead in our fields to the thought that there is significant dynamic topography. And of course, we even understand this technically, right? We have what we call so-called kernels. In the literature, they're often shown per individual degree. In a recent paper that Lorenzo and Zia have published, a really nice paper, they have plotted these kernels not just for individual degrees, but really for all degrees, degree 2 to 20, as you see here. And let's say there's a constant viscosity, you will see that these kernels depend very specifically on where density anomalies are located and which wavelengths they have. In particular, if you go to kernels that involve an astenosphere, in what form whatsoever, they have even crossings in the sign. And what the crossing in the sign mean is it is possible to place a density anomaly at a certain depth level and get zero contribution of it at the surface. And so it is clear that we need to think carefully in terms of global Earth models and in terms of boundary deformations and viscosity variations. And then I think much of the controversy of the existence of dynamic topography disappears. And this is a very nice last slide of their paper. There's a density anomaly simply placed visually here under Africa. And for the realistic model with the viscosity stratification, one of the things that I want you to realize is there's a dynamic topography still on the order of a kilometer, and yet there is zero free air gravity anomalies. Now, there's one more point that I wanted to make, because I think this is an important point to make. One of the reasons why these kernels are really interesting also for us to think in terms of time is you are aware that there is a non-uniqueness in the kernels and that there are many different viscosity profiles that can be used to fit the geoid. The reason, of course, is quite simple. When you have a density anomaly, you can trade the structure of the density anomaly if that is uncertain relative to the structure of the viscosity profile. If you had time-dependent Earth models, density anomalies would walk through these kernels depth-wise. And so that would significantly reduce the non-uniqueness associated with density anomalies. And this is a moment to say that, of course, these viscosity profiles have been studied in great care by Alex. I've waved to you, and the viscosity profiles that you guys have obtained really are in much detail informed by observations. So, why don't we do time? Well, of course, we don't do time because it requires initial state estimates. We have to start models from somewhere. And of course, one way to do this is the unknown initial conditions from starting convection models in the past can be overcome by several ways. The first one is to simply model the process that generates density anomalies, and that is, of course, subduction. And so if you run models in which the subduction history is brought in as an extra information from the outside, this is called assimilation. Then eventually this model will develop density anomalies, presumably reflecting the true state of density anomalies. The difficulties? Well, you have to do this for a very long time, going back in time 100 to 200 million years, and essentially only model the positive density anomalies. You don't model the negative. Of course, you could take advantage of all the great progress in seismic tomography and simply take state estimates of the metal from today and run them backwards in time, and this would be another way of predicting structures further back in time. And of course, the obvious last way is to go a formal way and pose fluid dynamic inverse theories. And this is what we do largely in München. I show you that these equations are rather awkward. I could walk through, but I don't do this in my 24 minutes that I have. The main thing that I want to point out is a sign change in the adjoint equations makes these equations stable against backward advection. And so that means density anomalies obtained from a cost function for the present state can be used to be advected back in time and iteratively update the model. The way one would do this, and I have a few comments here, there's a state estimate of the present day state, and the present day state allows us iteratively then from cost functions to update the initial state. And this is much better pictured graphically, and this is a slide that I like very much from Alex Fournier. He has a review paper on this for the dynamo models. And basically what you're seeing is, rather than a sequential assimilation which propagates information into the future, this is an iterative procedure. And basically it propagates the information backwards in time, and it can do this repeatedly against the same observation. And so eventually, iteratively, you fit the model trajectory to the state. Now, recently we have advanced this theory, and specifically we have accounted for the effects of compressibility, and this is work that has been done by Zia, and it's a very nice extension of the theory, a much more broad and applicable form of the extension of the theory than the simple incompressible adjoint equation that I showed you, which are now well over a decade old. How do we test this? Well, we test this by doing twin experiments. And twin experiment is a nice way of really saying, let's completely theoretically test how this works. I could say, I have a reference model. The reference model I know perfectly. I know its beginning, I know its end. And in this case, for example, we take a beginning state. There's a small little baby plume, you could call this potentially. And after about half a transit time, that baby plume transverses through most of the mantle. Right? This is done at very low resolution, at a Rayleigh number of around 10 to the 4. And this allows me again to make a remark, right? Because a naive way of looking at it is saying this is a simple computational problem. But what the adjoints are really doing is they are correcting for the adverse effects of diffusion. Now, in this model, because of the low Rayleigh number, the diffusion effects are 5 orders of magnitude larger than they should be, which means effectively this is a difficult experiment. And so what this then means is, let's take your reference state, as I said before, and make an experiment in which you're trying to recover an unknown initial state for the very same model. Now, since the state is unknown, what can I make as an assumption for the initial state? The best assumption I could make is the initial state is the final state. Now, if the final state is the initial state, then the model will produce a final state that differs from the true final state, and that's fairly clear. I start from something different, and I end with something different. Now, if I iterate this procedure several times through, after 6 iterations, this is the recovered initial state, and this is the recovered final state. And this is, if you remember, your reference model. Plotted on the right column is the error, and the main thing that I want to point you out is the error is on the range of about a few % relative to the lateral temperature variations. This is a more technical way. You can cook what is the RMS error as a function of the iteration, and you see there's a very nice conversion both in the final and the initial state. Regularization through the surface velocity field, right? This is an important part because what this really says is, I find this very unintuitive. We all know that that convection is a chaotic process. It shouldn't be possible to simply get back in time. So the question is, why does it work anyway? And so the way technically to approach this again is to do again a twin experiment, the state A, B, C. You run this about for half a transit time again in a simple model. And now I make a different assumption for the initial state, and the assumption that I make is there is no convection in the initial state. Okay, that's a drastic way of approximating the initial state. And this is very unrealistic. So again, after a number of times, now iterating back and forth, but doing 2 different classes of models. One in which the surface velocity field is known, and the other one in which the surface velocity field is not known. This is a free slip model. This is a model in which the surface velocity is explicitly stored from the forward run and then let evolve in the adjoint procedures as an additional form of information that gets into this. This is the reference state, just for you to remember. And now see what happens, right? If you do this for an unconstrained model, you will end up with spurious subduction zones that don't even exist in the real model, right? Here, right? And so clearly, you can make it very explicit, not converging. And here's again the errors, and for the free slip model, this model diverges. For the no slip model, the error converges. And actually, technically, this is nice too. We can relate this to a mathematical theorem by Serene, a mathematician in the 50s in Chicago, that relates the predictability of flow to the knowledge of the surface velocity fields. So that means, oh, and by the way, another point too is, note that even though the initial state does not converge, the final state still converges. You still end up with a model that fits your final observation, even though the reconstructed initial state is incorrect. Now, of course, things to work for. Carolina, for example, early on, but later also in the Sydney group, we do have reconstructions of the surface velocity field. And one thing that I find very nice as a theoretist is, for us, reconstructions of past plate motions become effectively a representation of Serene's uniqueness theorem for flows. And so, then let me quickly come to the effects of compressibility, because adjoints, of course, should eventually be applied to seismic tomography models. Seismic tomography images the mantle. The mantle is compressible. So let's see what happens when you do this in an inconsistent way. What if you took the simpler, incompressible adjoint equation that I showed you before and applied them relative to a twin that includes all the effects of compressibility? That means effectively it would be taking, for example, the incompressible adjoint equations and apply them to the Farallon slab. Again, we have a reference model. The reference model has an initial state and has a final state. And now we have twins. This is a twin that has all the effects of compressibility in the new theory included. And rather than showing you all the iterations, I simply show you this is the reconstructed best guess for the initial state and the final state. And this, of course, would be the correct representation of the theory. And now let's quickly jump to the incorrect representation of the theory. You end up with spurious artifacts of density anomalies in the mid-mantle. The reason why this is important is if we wanted to reconstruct shorelines, Alex, then the amounts of density anomalies that are spuriously present in this would degrade our fits. It's very clear that we have to be very careful of how we apply this kind of theory. And again, this is the final state. The final state always converges, of course, with the inconsistent formulation. It converges not as well, but it's really in the initial state that you see again that you end up with inconsistencies. And so what you want to use, of course, is the consistent formulation. This is an error representation, and the error representation, again, in the consistent formulations are very small. So this is all good. These are very simple, incompressible, purely synthetic models. Can this be applied to more realistic, larger scale geodynamic Earth models? And again, do we understand the effects of uniqueness model initializations well? Well, this goes to the question, first of all, is this computationally possible? But also, what classes of forward models would we be using? And so the classes of forward models that we want to use, or that we should be used, really at the moment in geodynamics are unclear. We have very different and diverging opinions on what kind of mantle convection models we want to involve. They could be, for example, layered in convection. They could have large piles at the base of the mantle. They could be in a pyrolite composition. There are very diverging opinions in the literature on this. I put this slide up because I think Bernhard has done a very nice job in the last decade or so, really to try to think very technically, what is it that a convection model needs to generate as a seismic observable so that it can be explicitly compared to a seismic observation? And so this involves, for example, thinking very carefully about the effects of seismic filtering. It involves, for example, propagating seismic waves through a convection model to generate synthetic seismograms, all of which then can be compared technically to an observation and lead us away from the simple red and blue comparison that we often tend to do, but that we're now really beginning to extend, I think, far more in a technical way. One of the conclusions that Bernhard came up with, and I think this is something that I certainly subscribe to, is that a pyrolite composition is a reasonable assumption, and at the same time, that these models would eventually draw a significant amount of heat from the core. So these models really do have a significant amount of density anomalies generated that have nothing to do with the history of subduction. So that's really important. And so let's look of how one would go about this. In this case, the final state is taken as a representation from the tomography of Steve Grant. And if that model again iterates back and forth, there are about 80 million grid points in it. There's a simple 3-layer viscosity profile. And the assumption for the state 40 million years ago is again what I've done you earlier. It simply assumes 40 million years ago the mantle looked exactly like today. Of course, if we make that assumption, we will have to iterate, and eventually the model state will change. There are small changes in the course of about 7 iterations to the final state of the model. More interesting is how the adjoins really do this technically throughout the model, right? And so this is the correction that are applied iteratively, and the two things that I want to draw your attention to is, first of all, if you start off with the structure of the mantle today as a representation for the structure of the mantle in earlier times, it means you will have radial location differences. Things rise and move. So what the adjoins really should do is they should radially correct where the heterogeneities go. And so, for example, in the case of the African plume, this comes out very nicely, right? Temperatures are reduced in this region, but they're increased in this region. So you can really see what the adjoins are iteratively doing. Another thing that you see also is what the adjoins are really doing is they are generating, in particular, corrections in the thermal boundary layers. And that is why we need to be so careful in using a complete theory, because it's in these boundary layers that we really need to provide the largest corrections, and that's where the theory really comes into its own. After the second iteration, there are still large corrections, but look, after iteration 7, we're largely done with all the corrections that we wanted to do. And this is the predicted initial state of the model. And the main thing that I want you to appreciate, even for these last 40 million years, there are significant variations of the initial core mantle boundary structure relative to what would be the CMB structure today. And I think this is the one here that I want to show, and I'm apologizing that I do this too quick. So, model initialization. Now we no longer have a twin experiment, right? Because this is a seismic model. We do not know what the Earth looks 40 million years ago. So there's no way of doing this with a twin experiment. So the one thing that you can still do, of course, you can still go and say, well, let's take different first guesses. Let's say the mantle at 40 million years looked like tomography. Let's say the mantle, which is really drastic, looked like tomography but rotated 90 degrees. Let's say the plumes are under America and the slabs are in Africa. Let's say there is no convection in the mantle at all. There's just 0 lateral temperature variation. You've seen all of these in the previous simple experiments. But now really we do this at full-blown geodynamic models. Also, let's say you do a backward convection first to generate an initialization that then could serve as a start. Personally, I've never understood this mathematically, but I point you to an artifact that happens. If you take a backward advection, it means the East Pacific rise turns into a ridge. And so you have a subduction zone in the middle of the Pacific. It also means that, for example, in the middle of the Atlantic, you would have a subduction zones. Ridges turn into subduction zones, and subduction zones turn into ridges. So I don't think that this is actually a good way of initializing the models. So no matter what you do, this is the reconstructed final state for all these different first guesses. And I leave it to you to decide that they're basically largely identical. No matter what I did in the first place, I always end up with the same final condition. This is again plotting the errors as a function of adjoint iterations, Gesundheit, and you will see for the whole mantle, but also for the upper mantle. And the main thing to point out is, for example, in the terms of the backward advection, you incur significant errors in the upper mantle. So, this now allows me to go to the last part of the talk. I hope I am 1 minute. Okay, good. Very thank you. And now let's up this up one more time. Let's do not take this with 80 million grid points, but with 670 million grid points. And those of you that do this business will realize this is painful, because even making pictures at that resolution takes days. Model overview, 760 million grid points. There's a grid point distance of about 10 kilometers at the surface of the model. At the core mantle bound, it's 5 kilometers. I checked yesterday, it's 700 kilometers from Munich to Paris. It's about 70 grid points between here and there. So one iteration, even one iteration, is 1 million core hours. We run these models on 2,000 processors for 3 weeks solid. So now you understand why I have to be grateful to the Leibniz Rechenzentrum. 6 adjoint iterations is what I will show you. And of course, the point is not to say, there is the model and this is how it looks in the Eocene. The point is to say, if we take different models, this is how they will look differently. There's a pyrrolite composition, again assumed for the sake of sensitivity. And in particular, I will want to know a little bit more about the effects of the tomographic input structure. Different tomography models are different. And the lower mantle viscosity. These are the 2 tomographic input models that we have chosen. One is by Afanasieff from the Zurich group. There's a natural reason why we take this model, because Lorenzo is involved in the construction of that model. And there is an S-wave model here by Simmons. There are 2 different viscosity profiles. And again, this relates to the thought that we're not entirely certain what values to use. Again, Alex would be the expert in this room and would have far more opinion. Simply here we take 2 different versions of that. And of course, if the viscosities are increased in the deeper mantle, it simply means the sensitivity in the surface topography evolution relative will be reduced. This is a conversion of the seismic anomalies to model density anomalies. This is a specific nod to Carolina and to Lars, because without your work, we would not be able to be as careful and really thinking what are density anomalies relative to seismic velocities. And so both of you are doing a tremendous service to the community. I show you the results at model iteration 6. Mind you, this is an iterative procedure, right? So it really now matters at which iteration I show you the convection model. And a very brief thought on the general classes of images that I show you. This is the final state temperature evolution of the models for the tomography model of Afanasieff and for the higher viscosity 10 to the 23 Pascal second viscosity profile. This is a plot of the velocities. And the main thing that I want you to see from the velocities are the large regions in the model mantle in which the velocities are relatively small. But then there are also regions, especially in the asthenosphere, in which the velocities can become very large, up to 15 centimeters. We use these very high resolutions and we use these very parameters that we're trying to make as Earth-like as possible, in particular because under these conditions, relating time in the models to explicit time becomes far more straightforward and does no longer involve a scaling. So, by the way, there's a comment that I want to make because I'm too nervous. You pointed out to the African convection cell, and I apologize that I'm too nervous right now. Velocities are very high in the asthenosphere. In fact, the largest in plate velocity is the surface. And that makes tectonically sense, right? It's the flow that drives the velocities of the plates. And maybe I'll just walk you ever so briefly through, and there's more information that you can really take from that, right? But for example, the main thing that I would like you to appreciate is the velocity and evolution of the upwellings in the mantle under Africa. But I also would like to point out that it really leads to significant bursts of velocity in the asthenosphere. And those of you that remember that 2 years ago I gave a talk in this very same Collège de France on rapid plate motion variations will realize why this is of interest. And of course the evolution of the dynamic topography. So I have a few seconds left for Europe. Because obviously, right, I want to show Europe. This is the Iceland plume. And so look, it is rising up as one form of it. And again, look at the velocity fields here in Europe and look at the evolution of the dynamic topography in Europe. And some of you that follow this debate, for example, there's a lot of debate by our British colleagues on the rise of the British Dome. Those are very technical questions. I'm spending now a lot of time with my colleague Anke Friedrich at the Chair of Geology in Munich to very detailed, for example, look at the sedimentary evolution of Europe. This is a map for the Miocene. And because I'm not allowed to say anything more, and I agree with you, I fully, if I was the chair, I would do exactly the same thing. I leave you with that slide. This is the uplift history which I asked Zia, and it was very nice of you 2 nights ago, to plot it for Paris, right? Because this is convenient. But we could also plot this for Berlin, right? Because there's the DGG meeting in a few months from now in Potsdam, right? But almost all models predict a significant uplift in the last 15 or 20 million years. Geologists refer to this as the late Miocene uplift in Europe. And computational aspects I skip.
I think we have to.
And the conclusions you read.
Thank you very much. So.